In this video, I'm going to show how to balance an inverted pendulum using a car in a simulation and reinforcement learning. The agent that I'm going to use is Actor-Critic, and optionally, I'm going to do asynchronous parallelization or experience-based parallelization. So in general, this is a diagram of reinforcement learning agents. So they consist of a policy that, given an observation, is going to take an action, and a reinforcement learning algorithm that takes a reward and observation to train the policy. The reward and observation are generated by the environment based on the action taken by the agent. In this case, the reinforcement learning agent is going to be the Actor-Critic. And you can see in the table here, this is the one that we're going to use. It's good for discrete and continuous action spaces and observation spaces, and it does the training on the policy, unlike others that do it off policy. So all these pages I'm going to include in the description section. So as mentioned, it's good for discrete and continuous actions, observation and action spaces, but the action space in this problem is going to be discrete and the observation is going to be contiguous. The observation space is the position of the card and the rate of change of the card, the velocity of the card, and also the angle of the inverted pendulum and the velocity of change of the angle. The action space is going to be discrete. It's going to be either negative 10 newtons to the left or positive 10 newtons to the right. So as the name implies, the Actor-Critic agent is going to have an actor and a critic, and here's the formula, the name of the formula for the critic, the actor, which is pi, and takes as input for a given, the action is given for a given observation, which is called the state as well. So for the case of the critic is going to predict the expected long-term reward, the expected reward actually. Yeah, this is the long-term reward. Yeah, so it's based on the observation as well. So both of them are going to be trained, and the critic is going to help to train the actor as well. So computing the long-term reward is a central theme in reinforcement learning. Different agents have different formulas. This is the one that this Actor-Critic agent is using. And to train that, it is crucial to collect experiences, and they are in the form of observation, action, and reward. So you have a set of that trio: observation, action, reward, observation, action, reward, etc. So you get a batch of them. So for the long-term reward, it's going to use the reward collected so far, and then a discount parameter, a discount factor, is going to be used to decay the reward that you get in the future. The critic, which gives the B, is going to give you the predicted reward for the future. So you sum that over all the time steps, and yeah, it's given per state, per observation in here. Okay, so the purpose of the decay in the reward is because you want that the agent finish the task as soon as possible, and then you get the advantage function, which is basically subtracting this by the predicted long-term reward, and that is used for computing the gradient for the actor and computing the gradient for the critic, and you multiply that gain, that advantage function, by the action. So there's a pairing with the action and the reward, and you just sum that and get the gradient. The gradient is basically the vector in which there's a highest change. So you want to maximize the gradient, the direction of the maximum change, and that's going to give you the gradient that is going to be used to update the parameters of the actors. For the case of the critic, the action is not involved. In here you want to maximize the gradient because you want to maximize the reward, and here you want to minimize the gradient because you want to minimize the error in the prediction of the long-term reward. That's why you have only the long-term reward in here, the advantage function to the square. So with that you get the gradient, the minimized gradient for the critic, and you update the parameters for the critic. So that's about it for the Actor-Critic. So let's go and do the example in MATLAB. So first we're going to create the environment. So it's gonna have a gravity of 9.8, the mass of the car, the mass of the pole, the length, the maximum force, which we know is 10. The sample time, each step is gonna take 0.02, and this is a theta threshold. I understand that this should be the limit in the angle. It should not go beyond that. And this is the position threshold. It should not go beyond that in the position of the card. Either of the two thresholds being surpassed, then it means that you failed. And of course you get 1 point for each step that you don't go above the limits, and if you go up, beyond the limits, you get a -5 penalty. Okay, so let's change the penalty from -5 to 10, -10. So now it's -10, a higher penalty. So let's take the observation information from the environment. This is a method. This should be a method actually from environment. So if you do this, yeah, it's the same. These are methods from the environment. So the environment is ready to give you the observation info and also the dimensions and the action info as well. And the observation, as mentioned before, is going to be a position, the rate of change of position, angle, and rate of change of angle. So it's going to be a vector of 4. There's no limit, so it's -infinity and infinity. This is 4, the number of observation points. And for the action, it's basically a discrete value, which is -10 or 10. And this is to fix the seed for reproducibility in this example. Let's create the neural network for the critic, and the critic is basically gonna predict the long-term reward. So the input is the observation, a vector size of 4, and the output is gonna be a scalar, which is the long-term reward. We're gonna use 32 parameters for this network is very simple, a couple of fully connected layers and a ReLU for regularization. And then we take that critic network and we have to pass to we're going to use an RL value function to create the critic. And if you go to this page, which is going to be in the description, the page about reinforcement learning agents, you're going to see a table in here for all the agents. And this is Actor-Critic, and here you can see that Actor-Critic is going to use the RL value function. So that's the one that we use here. So the options are going to be the learning rate, 1 to the -12, and the gradient threshold to avoid gradient explosion. So it has a threshold of 1. So with the observation information, the critic network, we create the critic. Notice that to create the critic, we don't need the critic options. The critic options are going to be given to the agent itself. And for the actor, is going to be the input again, the observation, but the output is going to be the action. And you might wonder why not a scalar, why we have 2 values instead of 1. There's another article in the reinforcement learning documentation that mentioned that it's more efficient to have, if you can turn an output to be a category, then it's more efficient than just having a scalar. So in this case, we have 2 possible outputs, -10 and 10, so we can turn it into a category. So that's what we do. So you're going to have the probability for -10 newtons and the probability for +10 newtons. So this, according to the documentation, should be more efficient. Again, it's using basically the same simple architecture, a couple of fully connected layers with 32 parameters and a ReLU, the same learning rate and threshold, gradient threshold. And then we pass the observation. This one is the actions info because it's the actor, and the actor network. So we're going to use a discrete categorical actor because we have discrete actions, and also we're going to have a categorical output as well. So that's why we choose this one to create the actor. Now that we have the actor options, we have the actor, we can create the agent. So we have to create the agent options. The agent options are going to have the actor options, the critic options, and the entropy loss weight. The entropy loss weight is a parameter for the agent that encourages exploration. If you have it set to 0, there's no exploration. It's going to be totally greedy. And the higher, the more exploration. And exploration is important to avoid, because reinforcement learning can be seen as a search technique. And if you are greedy, you can fall into a local maximum. And when you add exploration, you can avoid falling into a local maximum, and you can find something closer to the global maximum. So there are different types of exploration. The most basic one is going random. The other one is basically trying to explore the areas that you haven't explored yet intelligently. Yeah, so we're gonna do some exploration, and this only applies for training. So when the agent takes the action, instead of taking the action that maximizes the reward, is gonna have with some probability some exploration actions. Yeah. So now you have the agent options. You have that carries the actor and critic options. Then you have the actor and critic. Then we can create our agent, and now we should be ready to train it after we specify the training options, which is gonna have a maximum of 1,000 episodes. Each episode is gonna have 500 steps. We're not gonna be verbose. We're gonna plot in a GUI the training progress, and we're gonna stop after the average reward exceeds or is equal to 500 for 10 straight steps. And just to visualize how the agent is being trained, we're gonna put this. And now with the training options, now we're gonna go to the parallelization. So this is an optional step. If you don't have parallelization or the parallel toolbox, then you don't have to do this step. This goes inside the training options. So there are two ways of parallelizing this. You're gonna have a set of workers, and the workers can compute the experience, or they can compute the experience and the gradients. In the case of the experience only, which is more convenient when the experience is the bottleneck, then the experience is computed by, let's say, 8 workers or 6 workers, and then the experience is sent back to the client, which is the one that coordinates the workers, and then the client is going to take those experiences, compute the gradients, and then will update the workers. In that case, that is asynchronous parallelization, which is what we have here, async. And in that case, it is recommended that if you have, let's say, 8 workers, maybe have 7 only. Use 7 because you need a worker or 2 for the client, because the client is going to do gradient computation. If the other alternative is using as async, just remove the A in here. In the case of synchronous, the workers are going to compute both the gradient and the experience, and that's called gradient-based parallelization. And in that one, you don't need to reserve a worker for the client. So the workers do most of the job, and that is synchronous because once all the workers finish computing their gradients, the gradients are going to be received by the client. The client is going to average them and update the network parameters, and then update back the workers. Okay, so in this case, we're going to use asynchronous. And you're going to see here that now we have parallel, and here you have the sync or async option. Okay, now let's run it. So the training should go faster because we are doing parallel training. It's going to take a while to load. Okay, started training. As you can see, the reward is initially very low, like 60. Actually, for some reason, it doesn't show in here moving, but it will once we finish the training. So it's gonna, once we have 1,000 episodes, or the reward is about 500 for 10 straight steps, it's gonna stop. Okay, finished training, and it took only 2 minutes. Very fast with parallel training, and it arrived at 500 reward for 10 straight steps. So we can close this now, and let's go back to try the train agent. So let's open the plot again, and we're gonna set the simulation steps. The original amount was 500, but let's set it to 1,000 to see if it's able to stand all this time. And there are some other options maybe I can play with, and it's gonna receive a point for each step that in which the pendulum doesn't fall. So the expected reward out of this is gonna be 1,000. So we're gonna simulate, and So really this simulation is a method of the environment. So I'm gonna use it as a method, passing the agent and the simulation options. This is a train agent that we just trained in here, and gonna get experience, and from the experience the experience gonna have a field called reward, and the reward has a method called sum. It's used as a function in here, but again it's a method from the reward, and that's gonna give you the total reward. So let's simulate it, and whoops, let's simulate this and see how it goes. And it looks pretty good initially. I guess the more time, the harder it is to keep it balanced, but it's looking fine. Yeah, so it did pretty good this time. Last time I tried, it almost went out of bounds, but this one it did well. Okay, so now let's get the total reward, which is the out of the experience output. So yeah, so actually this is a method, so I'm gonna run it as a method. So yeah, the reward is 1000. So basically it was able to train it correctly and fast. That's the purpose of parallel training in reinforcement learning. Thank you very much for watching.